By the way, a brief message for future online students. What I said in lecture 3A, where I want to let you know that I'm praying for you, that's true for future online students as well. What I tried to emphasize here at the end of lecture 3A was that simulation is one thing, it's kind of cool. For a second thing, it can help produce understanding, at least if you think about it enough. Okay? And for a third thing, simulation is going to be a big thing for us in terms of developing our theory that we use later in the course to do what's called statistical inference. So these things that I'm doing with RAND are much more important than you might imagine. So it is worthwhile to pay attention to. For the fall 2015 class, as far as these quizzes have gone so far, you know, I haven't quizzed you on everything that I could have at this point. I could have had questions on this quiz, but I didn't. They might be on future classes' quizzes. I didn't for your quiz yet about density curves. I could have. I could have had the information from the previous half of class, lecture 3A, about density curves. Okay? It was also in the reading. I also could have emphasize these things in your quiz, but I haven't yet. Again, in future class, maybe I did. Future online or in-class classes, I could have quizzed you about these things. So these are things that still could show up on quizzes and still probably will show up on quizzes, just to sort of be a little hint on Thursday. Something related to this information and probably something related to density curves will show up on Thursday's quiz, and perhaps even future quizzes. Our main focus here, the second half of class, is to focus on the normal distributions and calculations with the normal distribution. And this is going to be the hardest subject yet. Okay? I think I better get the light for this. All right, don't look at your paper. You won't be able to see your paper very well, but hopefully you can see these numbers. Can you see these numbers that are green? Okay or not? Okay. This is a better picture of a normal curve that I found online than the one that I looked at last Thursday. Also called the bell curve. It's what's called a standard normal curve. It's centered at 0. And it's got a standard deviation of 1. Though you could also imagine these numbers on the axes as just representing how many standard deviations above or below the mean the data are. Notice that the one and -1, if you follow it up to the curve, it does hit the curve at what are called the inflection points, which is where the curve is steepest. Okay, if this was a hill to ski on, the hill is steepest here and there. Those two values are 1 standard deviation away from the mean of 0, 1 standard deviation higher than 0, 1 standard deviation below 0. Those are called inflection points. Another way to think about the inflection points is where the concavity changes. This part of the curve looks like a frown, right? This part of the curve over here and this part of the curve over here look like smiles, or parts of smiles. When it looks like a frown or part of a frown, that's called concave down. When it looks like a smile or part of a smile, that's called concave up. And the inflection points are where those change. And again, the point is those are 1 standard deviation above or below the mean. That's the meaning of the standard deviation when your data are well modeled by a normal curve. When a normal curve is a good model for the data, that's how you interpret the meaning of the standard deviation, how it gives meaning to the spread. If the standard deviation was bigger, then this curve gets more spread out. But the area's still got to be 1, so the curve would have to also get flatter. I wanted to illustrate that with Mathematica, but the Mathematica is not working yet. Notice that if you add these green numbers in these 4 middle blocks here between -1 and 1, 15 plus 15 is 30. 19.1 plus 19.1 is about 38. 30 plus 38 is 68. 68% of the area, and therefore 68% of the data are within 1 standard deviation of the mean. That's the beginning of that 68, 95, 99.7 rule. I'll say that again. Listen carefully. These numbers represent areas under the curve. This is a density curve. It's our most common density curve. You add up these areas that are between -1 and 1. 15 plus 15 is 30. 19 plus 19 is 38. 30 plus 38 is 68. About 68% of the whole area under this curve goes between -1 and 1, and that's the same approximately as the percentage of data that's within one standard deviation of the mean. That's fundamental importance, okay, that you understand that. We're going to use this more generally, though. We're going to calculate areas more generally using our calculator and a table. Here, by the way, is the formula for normal curves. You don't need to know that, but I put it on here anyway. I don't have time to explain this right now, have some graphs of density curves that are skewed. This one's called an exponential distribution. This one's called a chi-squared distribution. I don't want to take more than 2 seconds here with those today. I might talk about them later. Here's our main example for the rest of class today. Cindy scored 700 on the math part of the SAT score, while Bobby scored 28 on the math portion of the ACT. Assume that SAT math scores are normally distributed with a mean of 500 and a standard deviation of 100. Assume that a histogram of the data of people's scores is modeled by such a curve. Assume ACT math scores are normally distributed with a mean of 18 and a standard deviation of 6. A different normal curve when you look at the data for the ACT scores. What were the approximate percentile ranks for Cindy and Bobby? In other words, how well did they do? Were they at the 90th percentile, for example, meaning 90% of the people scored lower than they did? Or were they at some other percentile? Who did better, and approximately how high of an SAT score would put Cindy at the 99th percentile? That's our question here. I also have a harder question that we'll see if we can get to. Approximately what percentage of the SAT math scores are between 650 and 800? Anybody know about the Brady Bunch? Okay. Cindy and Bobby are from the Brady Bunch. There'll be lots of little cultural things in this class related to cultural things from the 60s, 70s, and 80s. You've heard of the Brady Bunch, haven't you? Okay, yeah. Anyway, so what's going on here? SAT scores are well modeled. The histogram for SAT data is well modeled by a normal curve, a bell-shaped curve, centered at 700, it says. Excuse me, 500. And with a standard deviation of 100, meaning this horizontal distance between the mean and the inflection points on either side is 100. Meaning this score down here is 400 and this score down here is 600. There are symbols for the mean and standard deviation here that are different than the symbols I've talked about so far. The mean is denoted with the Greek letter mu, and it looks like that. That's called a mu. Not mu, mu. It's a great Greek letter. Why do we call it mu? I guess it looks kind of like an M and kind of like a U, so we call it mu. Actually, I don't know if that's the real reason, but I like to pretend it's the reason. Okay? Mu is the Greek version of M, actually. It stands for mean of a density curve. And every density curve actually has a mean. Because the normal curve is symmetric, the mean is centered where the peak is. In the middle of the symmetry. We use a Greek letter for the standard deviation as well. The Greek version of S is sigma. Not that sigma, that's a capital sigma. We use a lowercase sigma, which doesn't look anything like an uppercase sigma for the standard deviation. It looks like this, and that's the thing that shows up in your calculator underneath the S, although we're still not going to use that. You're just being told what the standard deviation is. So for the SAT scores, your normal distribution that models the histogram looks like that. For the ACT scores, your normal curve that models the histogram is centered at 18, and the standard deviation is 6. Making this 12 and this 24. What do you need to do now? What's the question? What were the approximate percentile ranks for Cindy and Bobby? In other words, their scores were at a certain spot where a certain percentage of the scores were below them. Cindy scored 700. She did well. She was above the mean. On this scale, she was way over here. What's her percentile rank? Here's the key. Listen real carefully. The percentage of people who scored lower than her is the area under this curve to the left of 700, which is most of it. She had a very good score. Probably 95th, 96th, 97th, or 98th percentile, perhaps. I'm guessing. You get that? That's what the density curves do. The area under the curve approximates the percentage of the data in that range. We're talking about scores less than 700. So it's the area under the curve to the left of 700, which technically goes on forever, which would include negative scores, but don't worry about that. Don't worry about that. It's a model, it's imperfect. For the ACT, Bobby scored what? Bobby scored 28. Right about here, he was also a pretty high score. His percentile rank is this area. Are these areas the same? Probably not. But they both did pretty well. How do you actually find these percentile ranks? You've got to find those areas. Two ways to do it. One way with a calculator, but this is not something I'm assuming you're going to be able to always do on your calculator, or it might be different than mine. Or with a table. Everybody should be able to do it with a table. Let me show you how to do it with the calculator first, in kind of the best way perhaps. First, make sure your window is nice. And a pretty good window in this situation, let's see. We've got a pick here. We're looking at the SAT scores. So I'm going to pick an X-min of, say, negative 200, and excuse me, positive 200. And an X-max, symmetric about 500, that would be 800. Don't worry about the Y-X scale. What's the Y-min and the Y-max? Well, you could use 0 for the Y-min, it never goes below 0. How high should it go for the Y-max? The area under this thing has to equal 1. Okay, but this is a pretty big scale on the horizontal axis. The graph doesn't actually go very high. I might have to experiment with the Y scale to get it right, but let me just guess maybe 0.01. Let's see how that does. Maybe that's too small. Let me try 0.1. Don't worry about the Y scale. So go X-min 200, X-max 800, Y-min 0, Y-max 0.1. I'm not sure this is going to work real great, but let's see how well it does. Then if you've got this kind of calculator, I go to what's called distributions, D-I-S-T-R, which is above my bars button. I have to hit my second button feature. It looks like this for me when I do that. And I like drawing the area I'm trying to find, so I move over to draw. And this first option says shade norm. That means shade an area under a normal curve. I'm going to use that one. It needs some inputs. The first input will be the left endpoint of the area under the curve you're trying to find, and the second input will be the right endpoint. Now the left endpoint, well, what is that? It goes on forever in actuality. You could say it's negative infinity. But as a practical thing, I don't want to type that in. If I pick, there's so little area over here, if I pick 0, for example, that'll be good enough. Just pick something very far to the left there. Put a comma, then put the right endpoint, oops, comma. The right endpoint we do need here, that's 700. Cindy scored 700 on the SAT math course. That was her score. That's going to be the right endpoint that I type in. Then you put another comma. You put the mean of this distribution, which is 500. Then a comma and the standard deviation. 500, comma, 100. And again, the window, I'm not sure it's going to be the best graph, but let's just see what happens. Enter this now as is. Got it? Left endpoint, which again technically is minus infinity, but I picked 0. I could have picked something negative. Right endpoint 700, but you got to get that right. Mean is 500, standard deviation is 100. Enter this. And we're not going to get a real great graph. Oh, it's pretty low. Okay, I better use something like 0.01 to see it right. Okay, let me go back to my window and make this 0.01 and see if it looks a lot better. That's better. So it's shading the area. You can just barely see that it missed a tiny little area there. That's part of the area that wasn't shaded. The total area is about 0.977. Approximate that to 0.98. Cindy scored at the 98th percentile. About 98% of the people scored lower than me. What about Bobby? What's his percentile rank? Go back to the window. Pick a new window for the ACT one. Like say 0 to 40 maybe. And for the Ymin, Ymax, keep Ymin at 0. Ymax make it bigger than it is. How much bigger, that's hard to say. I'll try 0.2. You gotta look at the horizontal scale. Again, you want the area underneath the curve to be 1, the entire curve. I'm gonna guess 0.2 there and see how it does. Go back to distribution, draw, shade norm. I better pick something less than 0, I think, for the left-hand point this time. I'll try like -1,000 or something. Okay, it doesn't need to be that extreme. Right-hand point, though, needs to be 28. That's Bobby's score. This is a normal distribution centered at 18 with a standard deviation of 6. So the 18 and 6 need to go in. This is going to be a pretty big area as well. Probably above 0.9, maybe above 0.95. I think Bobby didn't do quite as well as Cindy. Here we go, ready? Picked a pretty good window. Yeah, he didn't do quite as well. That area is 0.95. He was at the 95th percentile. So even though they took different tests, this is a nice way to compare them based on the mean and standard deviation. Cindy scored at the 98th percentile, Bobby scored at the 95th percentile. Cindy did better than Bob, even though they took different tests. Get the idea there? How do you do this with the table? You have to first compute something called a z-score. The formula for the z-score is to take the data value minus the mean and divide by the standard deviation, like that. This does what's called standardization. This standardizes the variable. Essentially, it tells you how many standard deviations you are away from the mean, positively or negatively, above or below. If you get a positive z-value, that's above the mean. If you get a negative z-value, that's below the mean. In Cindy's case, you get a nice number here. You get 700 minus 500 divided by 100 is 200 over 100 is 2. Cindy, with a score of 700, was 2 standard deviations above the mean. The mean was 500, a standard deviation was 100. You go up 100 and then go up 100 again. I didn't draw this perfectly. I should probably put more over there. You've gone 2 standard deviations above the mean. That's why Cindy's z-score is a 2. By the way, mathematicians almost always put a little line in their z's, because otherwise people might think it's a 2. Okay? So 2's I don't make with a little line. Z's I do make with a little line. And that's pretty common for mathematicians and statisticians. Okay. If you make your 2's like that, great. But I tend to make my 2's so they look kind of like z's. How about Bobby's z-score? He got 28. What's the mean for the ACT? It's 18. What's the standard deviation? It's 6. So the exact same formula in Bobby's situation gives us, what, 10/6, or 5/3, or 1.6 repeating, which is approximately 1.67. So that's another way to tell that Cindy did better. She had a higher z-score. She was 2 standard deviations above the mean. Bobby was 1 2/3 standard deviations above the mean. About 1.67 standard deviations above the mean. Can you find the percentiles without technology? Yes. And this is a big thing you need to be able to do in this course. You can use a table. Can I turn this off first? I get hurt. You can use table A in the front of your book bring your book every day, and your calculator every day, and your pencil every day. Table A, in the front of the book. This table, look at what it's giving us. I'll let you zoom in on the screen there. It's giving us areas under bell-shaped curves, under normal curves. In fact, this is what's called the standard normal curve. To the left of various numbers, the areas that are shaded are to the left. These are little z's here, by the way. You can barely see. That's what this table does. Tables in other books don't always give you the areas in this way. This is what our book does. Areas to the left of any given number. For example, the area to the left of 2 can be found by first looking for positive 2.0. What is 2? 2 is 2.00000. The hundredth spot is 0 as well. Look at where this row and this column meet, right there. Zoom in if you need. It's pretty small for your eyes, I think. 0.9772. If you can see that in your book, that's good. Might be bigger in your book. 0.9772. That's Cindy's percentile, 98th percentile. That's the area under the curve to the left of Cindy's 700 score. Based on the standard normal curve that's got a mean of 0 and a standard deviation of 1. What about Bobby? Bobby had a z-score of 1.67. So look for 1.6. Look for 0.07. They meet right here. 0.9525. About 95th percentile for Bobby. So we're confirming what we just found. Okay, real quick. How do you find answers to the other questions? Can we do it in 2 minutes? Approximately how high an SAT score would put Cindy at the 99th percentile instead of the 98th percentile? The formula right here can be solved for x using a little algebra. Multiply both sides by sigma to cancel the sigma on the right. Then add a mu to both sides to cancel the mu on the right. And you'll get the equation x equals mu plus sigma times z as another form of that exact same equation. Essentially, its inverse function, if you will. And since we're talking about the SAT scores, the mean is 500 and the standard deviation is 100. We can write this as x equals 500 plus 100 times z. If we can find the z value corresponding to the 99th percentile, then we can use this formula to figure out what score Cindy would need to be at the 99th percentile. Going back to the table, which of these areas is closest to 99%? 0.99, zoom in real close. This one right here is, look in your book, 0.9901 is what that number I circled is. That's the one that's closest to 0.99. It corresponds to a z of 2.33. So plug in 2.33 into this equation. .33 times 100 is 233. You get 733. She'd need a score of 733 to be at the 99th percentile. We're about out of time. Let me just say for this harder question, if you use the technology, the calculator, it's actually easier than saying the harder question. You find the area between 650 and 800 rather than say 0 and 800. If you use the table though, it does become harder. To find this area, you end up having to subtract areas. There are examples like this in the book, and you should make sure you look at those. Also, give me 10 seconds, on Moodle there are links to miscellaneous videos besides our lectures. And ones that I put on there include more normal curve examples that I did. A lot more examples. You can watch those. Okay? See you later.